Okay, so I'm going to give a little talk about metal-organic supercontainers, MOSCs, and TNC, which is the tetranuclear complex. I'll tell you what that is in a second. So my motivation was mainly to learn a little bit about MOSCs, but also, I guess my main goal was to get a little bit of computational background because I really don't know how much of that works. So I have a visual representation of the MOSC molecule, but really it's kind of hard to work anything with a MOSC because it's so big and there's too much to it. So I focused on the tetranuclear complex for most of it, and so I worked on what happens if we change the metal, kind of. And so I have structures of the orbitals, the absorbance, and the states. So first of all, just what exactly is everything? So the first one that I have on the left-hand side here would be TBSC, and that's just the precursor to the whole thing. So we worked to synthesize that, and then we combined that with our metal ions. So the metal ion I chose was nickel, and we get a tetranuclear complex out of that. And then when combining that with a ligand, which would be like, this would be like the ligand holding the tetranuclear complexes together, you get the whole MOSC molecule. So I guess with the MOSC, you got the endo and the exocavities. The exocavities would be that tetranuclear complex, and so there's binding studies that you can do with that, and then you've also got that inner endo cavity that can also do binding stuff, but we're focusing on the exocavity. This is the MOSC molecules, and let's see if I can get the video going here. So these are some videos of the molecule itself. I tried to make this on Gauss view and realized pretty quick that it just wasn't going to happen. Okay, so I ran a orbital, just a diagram. So you can see that with the homolimbo, you've got the big d orbital around the metal ions. Not a whole lot of difference here. And then I ran an absorbance spectrum too to kind of get a feel for it. And you can see with the upspin and the downspin, they're both pretty similar. I've also got the complete, and you can see that there's a, the main absorbance is around 700 in that area, and that would correlate with the red. Spent a lot of time trying to like line that up. I hope that looks all right. But with that, you can see it absorbs the red light. So on the other end of the color wheel there, you've got the green. So when it's absorbing the red, it's going to be reflecting the other side. So the molecule is going to appear green, and I have a picture of that I'll show later. I also did a little bit on the spin states for the density of spins. So with the nickel ion, you have 8 different electrons that can be anywhere within these 5 orbitals. So you've got the low energy and high energy orbitals. And so you've got both high spin and low spin versions of the same molecule. And so with the low spin state, you'd have more of your electrons paired, as with the diagram on the left here. I know this isn't the nickel, this would be iron, I think, here, but this is just giving a good idea of how it works. So low spin, you've got them all paired, and then with the high spin, you've got 4 unpaired electrons. And so we wanted to see what the difference would be between the nickel TNCs, where it would have the low spin, where it would be 0 unpaired electrons, and then also the high spin, so that each one would have 2 unpaired electrons. And so throughout the whole tetranuclear complex, since there's 4 different nickel ions, there would be 8 unpaired. And so here we ran a density of states. So we've got on the far left, we've got the 0 paired, or 0 unpaired, and then we've got the average here, and then 8 unpaired. And as you can see, with the 0 unpaired, you see kind of a bottom heavy, and then it evens out, and then you've got top heavy with the 8 unpaired. And then you've also got the energies on the bottom here of each one. They're actually pretty close, which is a little surprising, but you can see that the average is actually closer to the 8 unpaired, so it's going to be closer to the high spin than it will be to the low spin in a normal state. And then here is my conclusion. I guess that image didn't show up very well, but it's supposed to be showing that it's just green. So I got the computational characterization of MOSC is pretty stressful, so there wasn't much we could do with that. We did find out though that the nickel absorbs around 700 and appears green because of that, and also that the average spin is close to the highest, or average state is close to the high spin than low spin, although it's very close.
Okay, but thank